Okay, so today we'll be going over section 9.7 and we're going to be talking about Taylor and Maclaurin polynomials. Maclaurin and Taylor polynomials. So to begin with, to start this up, what I'd like you to do is go and do this problem on your own. Pause the video, remind yourself on how to find the equation of a tangent line, and return when you've come back. I'm sorry, return when you've finished. Okay. So we went over this last semester. We haven't used this too much this semester, but to find an equation of the tangent line to the curve y equals e to the x at the point 0, 1, you need two things. You need a slope and a point. I've given you the point, 0, 1, and next we need the slope. The slope comes from the derivative. Right? So y prime is equal to e to the x. And so what this is a formula where you put in the x coordinate of the point, and what comes out is the slope of the tangent line at that point. So the slope for our problem is to take y prime and evaluate it at our x coordinate, 0. And that will be e to the 0, which is 1. So now we have our slope is 1 and our point is 0, 1. We can use the point slope formula and write this as y minus y is equal to my slope, 1, times x minus 0. So this is y minus 1 equals x, and this is y equals 1 plus x. And you'll see why I've switched the order in just a little bit, but we want it in ascending order instead of descending order as we're used to in this section. We want these things in ascending order. It's going to make life a little easier, just a little. So here's the graph of the original function y equals e to the x, and the graph of the tangent line y equals 1 plus x. And again, just a reminder, one of the points of the tangent line is near the point of tangency. Your function and your tangent line have about the same values, right? They don't have the exact same values, but you can see that in this little interval right here, in this little region right here, they're about the same. Now, so all along right here, they have about the same value. Right now, as you move away, as your x values are over here, you can see that your outputs are nowhere near the same. So what we want to do is get a better approximation, right? And so the better approximation that we're going to want to make is by using higher degree polynomials, right? And one of the things that you should notice about the two functions y equals e to the x and y equals 1 plus x is that they have the same output at 0, right? So we'll call this f of x, and we'll call this p1 of x. And so p1 of x is the tangent line. It's a polynomial of degree 1. That's why this 1 is here, right? And what you should notice is that when I evaluate P1 at 0, I get the same thing as if I evaluate f at 0. F prime of x is also e to the x, and P1 prime of x is just 1. And so then what you can see here is that if I evaluate my derivative function at 0, I get the same thing as if I evaluate the derivative of my f at 0. So then that so another way of saying that is that the derivatives at 0 match, right? And so with that in mind, if we want to get a higher degree polynomial, what we might be inclined to look for is a second degree polynomial whose second derivative matches matches with the function e to the x. Now, what we would want then is for the output at 0 to match, so that they go through this point, the first derivative to match, so that it'll have this same um, steepness right here. But then if we make the second derivatives match, then we'll bend our polynomial to bend in the direction of this curve, and that's that's what we're going to shoot for. So that's where we're headed for now. It says find a second degree polynomial that has the same output at 0 as y equals e to the x, and for which the first and second derivatives at 0 match with y equals e to the x. So let's first figure out what are my first and second derivatives. So my first derivative is e to the x, and my second derivative is also e to the x. So we're looking for a second degree polynomial, and we're going to call this P2 of x. And again, we're going to write it in ascending order. So it needs to be a constant, C naught, plus a constant times x, C1 times x. And to help keep track of these, I'm going to let the index correspond to the power here. Plus a second constant, C2 times x squared. Right? Instead of using a, b, c, we'll just use c naught. The exponent on the x is 0, c1, the exponent on the x is 1, and c2, the exponent on the x is x squared. Now we want p2 of 0 to equal the same thing as my function at 0. And so then this will imply, now when you put your 0 in for x here and here, then both of those will go away, and you'll just get c naught equals e to the 0, which is 1. And then when you look at the first derivative, p2 of x prime, then what happens there is this constant term goes away. The derivative of this term is just c1, and the derivative of this term is 2c2, and don't forget to take 1 away from the exponent. So when you want your second derivative of x to equal your second derivative, when you want your first derivative of your polynomial to equal your first derivative of your function at 0, that means then that when you put in 0 in for x over here, this goes away. So this term will go away, and you'll just get c1. And then over here, you will get 1. And so then c1 is also 1. And next we need to find c2. And so then when you take p2 double prime of x, then you take the derivative of this expression right here, which will make this term go away. The derivative of x is just 1, and you just get 2 times c2. So when you want your second derivative at 0 to equal e to the 0, that will then tell you then that 2c2 has to equal 1, and so then c2 has to equal 1/2. And so then that means that your polynomial of degree 2 is 1 plus x squared over 2. Notice that the first two terms, 1 plus x, match the first two terms of the tangent line of the first degree polynomial, where the first derivatives match and the output match. And the only thing that changes is we just added a third term. Here's what this looks graphically. You can see that by adding this extra term, we extend the interval over which the polynomial and the function look pretty close. So we extend that interval a little bit, not a lot, but a little bit. that your curve now has the right bend, and so then this looks pretty good. So this is the y equals 1 plus x squared over 2, and this is y equals e to the x, and over here you have y equals 1 plus x. Notice that here we have 3 terms and here we have 2 terms. The first terms match, right? It's just that third term, we just added that extra term, and that helps give it the right bend. Still not great, so let's try this again. So find a third degree polynomial that has the same output at 0 as y equals e to the x, for which the first, second, and third derivatives at 0 match with y equals e to the x. So you might want to try this on your own. It's a good time to maybe pause and get comfortable with what we're doing here, and then come back. So again, y prime equals e to the x, y double prime is also e to the x, and y triple prime is also e to the x, and they match, right? We need some space here. Let me go ahead and do that. Now we're looking for a third degree polynomial, so we're going to call that P3 of x, and it's going to be a constant C0 plus a linear C1x plus a quadratic C2x squared plus a cubic C3x cubed. To figure out my constant, I want the output at 0 for this polynomial to be the same thing as the output at 0 for my original function, right? And so then that's going, if when I put in a 0 everywhere I see an x, I will get just C0. And when I put a 0 for the original function, I will get e to the 0, which is 1. So C0 is 1. When I want to find my C1, I can look at the first derivatives and make them match. So my first derivative the constant term goes away. For this term I get C1. That's the only one that will not have an x. For the second one, I will bring down the exponent, take 1 away from the exponent, bring down the exponent, take 1 away from the exponent, and you will see then that the only one that does not have an x is this first one. When you put in 0, then this term and this term and this term will go away, and you'll just get C1. And when you put in 0 into the derivative so that they match, when you put the 0 into this one, and then you will get 1 again. And so then C1 is 1, matches the tangent line, right? And so then to find C2, again we look at the derivatives, find the second derivative, and then this term goes away. The derivative of the second term is just 2C2. And then the derivative of this one is 6. C3 x. And again, when I put in 0, this term will go away and I will get 2C2. When I put 0 into my second derivative over here, I will get 1 again, and this will tell me that C2 is equal to 1/2. And then finally, to find C3, we make sure that the third derivatives match. So we look at the third derivative. Change this to a 1. That should have stayed at 3. Apologize for that. So then the third derivative, then this term goes away because it's a constant, and I just get 6C3. So then for my third derivatives to match, my third derivative of this one is always 6C3. So this has to equal 1. So then C3 is 1/6. And so then my third degree polynomial P3 of x is 1 plus x squared over 2. Notice that that matches the second degree polynomial we got in the last problem. We just added a third term. By adding this third term, x cubed over 3, we guarantee that the third derivatives match, x cubed over 6. And there we go. Here are the pictures. Here's the second degree. Y equals 1 plus x squared over 2. And this is y equals e to the x. And now you can see that we've extended the interval over which these things are really close together a little more by adding this third term. And so then here we have this one here is y equals 1 plus x squared over 2 plus x cubed over 6. Okay, and so we see that we made this a little better by adding this extra term. We've extended the interval over which the graphs look relatively close. Obviously over here to the left, the e to the x is staying up here close to the x-axis, and the x cubed goes down here. So again, then what we could say is, well, let's add more. And so here we're just getting a little tedious. And so then rather than starting all over, we'll notice that the constant term, the coefficient of the linear term, the coefficient of the quadratic term, and the coefficient of the cubic term should be the same. All that we need to find now is the coefficient of the fourth power term. And we get that by taking the fourth derivative, right? And so then again, for this particular function, not for all functions, but for this function, e to the x, the first derivative is the same as the function. The second derivative is the same as the first derivative. The third derivative is the same as the second derivative. And the fourth derivative, which we said we were going to write with a little 4 here, is going to be the same as the third derivative. Right? So at least that part of it is simple. Very easy to find those derivatives. The fourth degree polynomial will look like this. P4, because we have fourth degree. And so then this will be a constant C naught plus C1 x plus C2 x squared plus C3 x cubed plus C4 x to the fourth. Okay? And again, if I take the first derivative, the constant term goes away. We get C1, and then plus 2C2 x, take one away from the exponent, plus 3C3 x squared, and then plus 4C4 x cubed. When I go to make my first derivatives match, all of these terms will go away. I will just have C1, so then C1 will be 1, just like we had before. When I look at the second derivative, then the C1 goes away. I get 2C2, same as before, plus 6C3 x plus 12C4 x squared. And when I go to make my second derivatives match, all these second terms go away. I'm sorry, all these terms will go away. We'll just have 2c2. It will still equal 1 because all my derivatives at 0 are 1, and we'll get the same c2 1/2. When I go to find my third coefficient, c3, I will need the third derivative. And when I do that, this term will go away. I will get C3 plus 24 C4x. And when I go to find C3, then I will plug 0 in for x. The only term that will be left is this 6C3, which is the same thing I had in the last problem. And my C3 will again equal 1/6. Okay. And so now finally to find C4, I'm going to take my fourth derivative, and this term will go away. I will just get 24C4. And so then C4 will equal 1/24. And so now then your P4 is equal to 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. If you notice, we just have one extra term than what we had before, this x to the 4th over 24. You can graph those on your graphing calculator and see what that x to the 4th over 24, that extra term did, and see that it made the curves a little bit closer together for a little bit longer. And there we go. Now we're going to want to do this for more than just e to the x. We're going to want to do this for some of the functions that we've come across. And so we're not going to want to do this same process that I've been doing over and over. We want to find some relationship between a formula for how to find these coefficients C0, C1, C2, C3. And so sometimes it helps to do a problem in general rather than a specific problem. Here we are working specifically with e to the x, and it's kind of hard to see a pattern. But if we look at a generic function, f of x, then it'll be a little easier to see the pattern. And so that's what I'm asking you to do here. Let f be a function differentiable n times at x equals 0. Find the constants C0, C1, C2, C3, all the way to Cn, so that the polynomial Pn of x, which is C0 plus C1x plus C2 x squared plus C3 x cubed plus dot 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 Cn times x to the n, matches f of 0 and f, the kth derivative evaluated at 0 for k is equal to 1, 2, 3, 4, 1, 2, 3, 4 all the way to n. Okay, so if you want your p to match your f at 0, well then when you put 0 in for x in p, all of these terms will go away. All that will be left is C0, and so then C0 will have to equal f of 0. That was easy enough. Okay. If you want your first derivative of this polynomial to match your first derivative of your function, if you want your first derivative of your polynomial to match the first derivative of your function, then what we can do to figure out what C1 needs to be is look at the first derivative. A lot of letters. Got to try and keep it all straight. So Pn prime of x is going to be, the C naught will go away. You will just get C1. And every term now will have an x. Every term to the right will have an x. 2C2 x plus 3C3 x squared plus 4C4 x cubed plus dot 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 dot. Then you will have n Cn x to the n minus 1. Then when you plug in 0 into your formula here, you will get, so Pn prime evaluated at 0, all of these terms will go away. The only thing that will be left is C1, and you will want that to match f prime of 1. I'm sorry, f prime of 0. You want them to match at 0, not 1. Okay. And everything will, so that's how you can find your C1. You're going to evaluate your derivative at 0. That will always be your C1. Now for C2, we do the same thing. We're going to look at the second derivative, because now what happens with the second derivative is that first term goes away, and this will be your first non-zero term, and it will just be 2C2. But then here you're going to bring down the exponent, 6C3x plus 12C4 x squared plus the next one would have been for C5. It would have been of degree 5, and you will have already have brought down the 5, and now the second time you're going to bring down the 4. So you're going to have a coefficient of 20. And then you'll have already brought down the 5 and the 4, so now you have 3. And on this last one, you will have brought down the n, and then now you have the n minus 1, and then you have the constant Cn, and now n minus 2. But when you go ahead and put in 0, and then the only one that remains is the 2C2, because all of these other ones will go away. And so then you'll want this to match with your derivative of your function, second derivative of your function, at 0. And then you can see what C2 is. C2 is the second derivative of your function, evaluated at 0. So C2 will be the second derivative of your function. You'll evaluate it at 0, divided by 2. Now, to find your third coefficient, C3, and you take the third derivative. So the 2C2 goes away. The derivative of 6C3x is just 6C3. And for the next one, you will bring down the 2. (24), and then C4, and then you'll take one away from the x. And so you just get x. For the next one, you'll have, you'll bring down the 3, and so you will have 60. you'll have the x squared, take 1 away from the exponent, plus dot dot dot. And if you look at this last term will tell you what's going on, right? First you brought down the n, and then you brought down the n minus 2. And then you brought down the n minus 1. I'm sorry, I did that. Got carried away. N. First you brought down the n, then you brought down the n minus 1. Then you're going to bring down the n minus 2. And you're going to take 1 away from the exponent, and you'll have n minus 3. And you can see that you're just starting with whatever the exponent was, and then you brought down, you're going to keep bringing it down, and then this tells you what this number in front is going to be, right? And that's what we saw here. This 6 started out with a 3, you brought down the 3, then you brought down the 2, and then you brought down the 1, until you no longer had an x. So that's 3 times 2 times 1, and that's 6. That's 3 factorial. Same thing happened with the 2 and everything. And so then, and so this is the pattern that I was hoping that you would recognize as you did more of this. But this is getting a little tedious, so we're going to stop here once we figure out what C3 is, right? And so now to figure out C3, this is Pn. And so then to figure out C3, we're going to take my third derivative, evaluate it at 0, and again what happens is all of these terms that still have an x in it go away, and all you have left is 6C3. And so then this will have to equal my third derivative evaluated at 0. And so then C3 will equal my third derivative evaluated at 0 divided by 6, which is just, okay, so so there we go. So now let me show you the pattern, right? By writing all these down, right? So the whole point of this let me clear some space here. You can rewind and pause if you needed some of that. Okay, so my whole point here is that C naught was f of 0. Which is the same, well, my C1 was f prime of 0. My C2 was f prime of 0 divided by 2. And then my C3 was f double prime, f triple prime of 0 divided by 6. And it may not be obvious what the pattern is, but it turns out that this is f of 0 divided by 0 factorial, because 0 factorial is 1. This is f prime of 0 hello, hello? Hello? Okay, I think we're recording. So this is f double prime of 0. I'm sorry, so this is f prime So this is f prime of 0 divided by 1 factorial. And this one is f double prime of 0 divided by 2 factorial. And this is f triple prime of 0 divided by 3 factorial. You can see why that is, because as you were taking your derivatives, you were going to bring down the exponent, take one away from the exponent, then bring that down, and it wasn't until that term became a constant that it would not go away when you plugged in 0. So then you were going to divide by whatever power that was, factorial, to figure out what that corresponding constant was. And so then here's the result that you need to know, that your nth coefficient is going to be your nth derivative evaluated at 0 divided by n factorial. Right, so that's important. We're going to use that. Hopefully you can see where that came from. It's my goal to show you where things come from, not just here's how you do it, but in the end, that's what you need right there. Okay, so because of all that, we can make this definition. If f can be differentiated n times at 0, then we defined the nth Maclaurin polynomial for f to be Pn of x is just, your first term is f of 0. Your second term is f prime of 0 times x. Your third term is you take your second derivative evaluated at 0 and divide by 2 factorial times x squared. Your third term is going to be your third derivative evaluated at 0 divided by 3 factorial times x cubed, and so on until you get to n. Your nth term will be your nth derivative evaluated at 0 divided by n factorial times x to the n. Okay. So find the Maclaurin polynomial for the function f of x. So find the Maclaurin polynomial p sub 5. So we want the fifth degree Maclaurin polynomial for the function f of x equals e to the x. Okay. So we're just going to start all over here. And the way I like to do this is by making a table. Over here on the left, I have n. This corresponds to the derivative that I have taken. And we're going to start with 0, and the 0 derivative just means the original function. When n is 1, where that means the first derivative. When n is 2, that means the second derivative. 3, third derivative. 4, fourth derivative. And 5, the fifth derivative, because we have p5s. So then here we want fn of x, right? So that's just the nth derivative of the function that I'm working with. So if f of x is e to the x, the nth derivative, so the no derivative is just the original function, e to the x. But then the first derivative is also e to the x, and so is the second derivative, and so is the third derivative, and so is the fourth derivative. Got a little carried away there. And then what I need to do is evaluate my derivative at 0. And so then these are always going to be 1. And that will then allow me to find my Cn, my nth coefficient, which is given to you by the formula that I gave you, that your nth coefficient will always be your nth derivative evaluated at 0 divided by n factorial. And so then 0 factorial is 0, so here you get 1. 1 factorial is 1, so here you also get 1. 2 factorial is 2, so here you get 1/2. 3 factorial is 6, so here you get 1/6. 4 factorial is 24, so here you get 1/24. And then 5 factorial is 120. Right? So then P5, which is what I'm asking you to find, is 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120. This table helps organize things nicely. And again, what is the point? The point is that near 0, this is approximately the same thing as e to the x. So you can put your numbers into this formula, or you can put them into this formula, and you get about the same thing. This is a much better approximation than the tangent line, and you can go out farther. Okay, so again, so find the Maclaurin polynomial, P sub n for the function f of x equals e to the x. So here what we want to do is we want to look for a pattern and continue the pattern, right? And so find a formula for it. So again, what we saw is that e to the x was approximately 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120. And rather than keep going on, we'll just put plus dot dot dot. And again, your e to the x, your nth derivative is always going to be e to the x. And when you put in 0, you'll always get 1. So your coefficient for your nth term is just going to be 1 over n factorial. And notice that we can write this in summation notation. And this is the summation from k equals 0, because my exponent starts at 0, then 1, then 2, then 3. So I will start this at 0. From k equals 0 to n of x to the k, x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, x to the 5, so it's just whatever k is, all divided by, and in the denominator you have k factorial. And this is one of the reasons why it's important for 0 factorial to not be 0, but for 0 factorial to be 1. I couldn't do this if 0 factorial were 0. I couldn't write that. We defined it that way, and then we're good. Okay. Find the Maclaurin polynomial for the function f of x equals the sine of x, P8. So we want to find P8. So again, you should take a moment to try this on your own. N fn of x, and you know, if you needed a little start, then you just once I make the table, if you can take it from there, pause it from there. If you don't need the start, just start from wherever you feel comfortable. But then we need to know what is the output for the nth derivative at 0, and then that'll allow us to find Cn, which is just fn of 0 divided by n factorial. So when n is 0, we're just looking at the regular sine function. And the sine of 0 is 0. And so then C0 is 0. When n is 1, the first derivative is the cosine of x. The cosine of 0 is 1. And so then C1 is 1 over 1 factorial, which is 1. When n is 2, the derivative of the cosine is the negative sine of x. Evaluated at 0, you get 0. And then, so then C2 is 0. When n is 3, the derivative of the negative sine is the negative cosine. Evaluate that at 0, and you get negative 1. And then So then C3 will be negative 1 divided by 3 factorial, negative 1/6. When n is 4, you get the derivative of the negative cosine is the sine of x. Evaluate that at 0 and you get 0, and C4 is 0. And I need to go all the way to 8, but I don't have any more space. But we're right back with my derivatives where I started, right? And so then there's really no need to continue the table. We can just go ahead and follow the pattern, right? This is one of the reasons why I went over pattern recognition when we were talking about sequences, right? So that you can follow the pattern, right? So then P8 of x, so your constant term is 0, so C0 is 0, C1 is 1, so that's x, 1 times x. C2 is 0, C3 is minus x to the third over 3 factorial. And then C4 is 0, but then C5 is going to be 1, and so then it's the coefficient of x to the fifth divided by 5 factorial. C6 will then be 0, because that's the pattern you should notice here. There's 0, 1, 0. Right? The next one will be minus x to the seventh, and you're either going to get 0 or 1, so then this will just be 0 factorial. And then plus x to the, then you're going to get a 0, so this is it. The eighth coefficient is 0. And again, it's very important to keep in mind what's the point of this. The point of this is that this is approximately the sine of x. Very similar problem. If you didn't try the last one, you should definitely try this one. Find the Maclaurin polynomial for 8, right? So n fn of x, fn of 0, cn, which is fn of 0 divided by n factorial. When n is 0, we just have the cosine function, we just have the original function. When you plug in 0 into the function, you get 1. And so then your C0 is 1. When n is 1, you get the negative sine function. But when you plug in 0, you get 0. And so then C1 is 0. When n is 2, you get the negative cosine function. And when you plug that in, you get negative 1. And so then you get C2 is negative 1 over 2 factorial. For 3, you get the the sine of x. And then you're going to get 0 here. When you evaluate the sine of x at 0, you get 0. And then C3 is 0. For 4, the derivative of the sine is the cosine. You get back to where you started. You get 1 over 4 factorial. Now we're ready to write P8. And that will be 1 minus x over 2 factorial plus x squared. Sorry, this should be x squared. It's C2. C2. C1 is 0, so the coefficient of the linear term is 0. C2 is negative 1/2, and that's the coefficient of the x squared. C4 is plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. If we just follow the pattern, it's just going to keep going plus minus, and you're always either going to get 0 or 1. So then plus x to the 8th over 8 factorial. And again, this is approximately the cosine of x. And the closer we stay to 0, the better the approximation. Okay, well, not all functions are defined at 0. The natural log is not defined at 0. And so Maclaurin polynomials don't exist for all functions. On top of that, we saw in our work last semester that sometimes for a tangent line, rather than getting a tangent line at 0, it's more convenient to get a tangent line at a point that's closer to some other point that we want to approximate, right? And so we don't always want to find our tangent lines at 0. So that's where Taylor polynomials come in. So let f be a function differentiable n times at x naught, not at 0. Now it's at x naught, some generic number. Find a polynomial that matches f of x naught and that matches the kth derivative at x naught for k equals 1, 2, 3, and n. Now the approach here is that what was nice about 0 is that all our terms went away when we plugged in 0 except that first term that didn't have a variable in it. But now we have this x naught, so if we stick with a polynomial like we had before, if we start with the same kind of polynomial, C1 plus, C naught plus C1x plus C2x squared, then plugging in the x naught is not going to make the terms go away necessarily. But what we can do is we can let Pn of x be a polynomial in x minus x naught, not in x. So it will be a constant term. Plus a constant times, instead of x, we'll do x minus x naught. And the usefulness of this is now when I plug in x naught for x, this whole term will go away. Plus C2 times x minus x naught squared plus C3 times x minus x naught cubed plus dot 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 Cn times x minus x naught to the nth power. Now to find C1, we substitute in x naught. Now to find C naught, we substitute in x naught. And you see what happens very nicely is that all of these terms that have an x minus x naught go away. And so C naught and so for this to match f of x naught, this will have to equal f of x naught. To find C1, we look at the derivative, right? And so then Pn prime of x, now this first term goes away because that's just a constant. Now we have this constant times this, but the derivative of this is 1 because the minus x naught is a constant, so we just get c1. And for this one, it's a composition, so we bring down the exponent. The c2 is already there. Take 1 away from the exponent with the same inside, times the derivative of the inside. So when we take 1 away from the exponent, but the derivative of the inside is 1, so we don't have anything new. Same thing is going to happen with this term. We're going to bring down the exponent, 3c3 times x minus x naught. Take 1 away from the exponent, times the derivative of the inside, but the derivative of the inside is 1. Plus dot dot dot. For the nth term, we're going to bring down the n. Cn. Take 1 away from the exponent, times the derivative of the inside, but the derivative of the inside is 1. And so then to figure out what C1 is, we'll evaluate our derivative at x naught, and we will just get C1. And then this will, so that the derivative, because all of these terms right here will go to 0. And so that this matches my first derivative, I will just set C1 equal to the derivative evaluated at x naught. And you can see that this is going to work the exact same way. And so then the point is your CNs are going to be the exact same. Your CN is going to be your nth derivative evaluated not at 0 but at x naught, and we're going to divide it by n factorial. It's going to work the exact same way. Only difference is you're now plugging in x naught. If f can be differentiated n times at x naught, then we define the nth Taylor polynomial for f about x equals x naught to be a polynomial in x minus x naught. And so then your constant term is just f of x naught. The coefficient of your linear term is just f prime of x naught times x minus x naught. And for the quadratic, it's the second derivative evaluated at x naught divided by 2 factorial times x minus x naught squared, and so on. And so then that is what a Taylor polynomial looks like. If you substitute in 0 for x naught, then you have a Maclaurin polynomial. So a Taylor polynomial is just a generalization of the Maclaurin one. So find the 4th degree Taylor polynomial for f of x equals the natural log of x about x equals 1. Again, pause the video at any point when you feel comfortable, and you can do this on your own, and then resume the video to make sure you did it correctly. We're going to do the same thing. We're going to make our table n, our nth derivative. Be careful here. You're not going to evaluate your nth derivative at 0 because it says about x equals 1. So you're going to plug in 1s, right? And then you can use that to figure out what your Cn is. And again, this is going to be your nth derivative evaluated at 1 divided by n factorial. So when n is 0, we always start at 0. You're just looking at the natural log function. And for the natural log function, you evaluate it at 1, you get 0. And so then your C naught, your constant term, is 0. When n is 1, now you're looking at the derivative of this, which is 1 over x, but for future derivatives, it'll be better to write it x to the negative 1. Then when you plug in 1, 1 to any power is 1. And so you get 1. And then your 1 divided by 1 factorial is 1. When n is 2, bring down the exponent, take 1 away from the exponent, when you plug in 1, you get -1. -1 divided by 2 factorial is -1/2. When you plug in 3, bring down the exponent, take 1 away from the exponent, and then when you plug in 1, you get 2. And then 2 divided by 3 factorial, which is 1/3. When you plug in 4, and then you get -6 x to the -4. When you plug in 1, 1 to any power is 1, and so you get -6. And so then you get -6 divided by 4 factorial. Now, 4 factorial is 4 times 3 factorial. Notice that this 6 right here came from bringing down the 1, bringing down the 2, and then bringing down the 3. So this is 6 factorial. And so then, I'm sorry, this is 3 factorial. And so then you have 3 factorial over 4 factorial. So that then becomes 1/4. Just trying to show you what's going to happen. -1/4. Find the 4th degree Taylor polynomial. And so then the constant term is 1. So P4. The constant term is 0, so there is no constant term. But it's a polynomial in x minus 1, right? And so then it's x minus 1. And your first coefficient is 1. And then minus x minus 1 squared. And your second coefficient is -1/2. And then it's plus x minus 1 cubed over 3. And then it's minus x minus 1 to the 4th over 4. Find the nth degree Taylor polynomial for f of x equals the natural log of x about x equals 1. So what I'm asking you to do there is look for a pattern for the terms. So Pn of x is equal to 1 minus x minus 1 minus x squared over 2 plus 1 minus x cubed over 3 minus 1 minus x to the 4th over 4. And you can see that this is alternating, and so that means that we have a factor of -1 to the power. But we start out negative, and so when n is 1, we start out positive, so we need an n plus 1. So that when n is 1, 1 plus 1 is 2, and this will be positive. They all have I don't know why. Let me see. Let me go back. My dyslexia kicked in, and I put x minus 1 minus x instead of x minus 1. So that needs to be fixed. All those need to be x minus 1. And so then they all have a x minus 1. For the first term, the power is 1. For the second term, the power is 2. That's about as easy a pattern as that can be. So we have n. And then in the denominator, Whatever the exponent is, that's what the denominator is. Even in this one, the exponent is 1, the denominator is 1. So then we have n. And then what we can do is we can write this in summation notation. So then we have from k equals 1 to n of, we have a factor of n minus, we have a factor of negative 1 to the n plus 1, which will make it alternate. We have an x minus 1 to the k, and we have a k on the bottom. And so there we go. And again, remember what the point of this is. The point of this is that this is approximately the natural log of x. So if I wanted to approximate, let's say, the natural log of 1.5, then what I would do is I would replace the x with 1.5. And you could use as many terms as you like to get an approximation. And find the nth Maclaurin polynomial and express it in summation notation for the function f of x equals 1 over x. Okay, so Maclaurin again means that we're going to evaluate at 0. So then we have n, we have fn, and then I think I'm going to need a little bit of room. Fn evaluated at 0, and then we have Cn. And so when n is 0, you have 1 minus x to the negative 1. And that will make it easier to differentiate so that I don't have to use the quotient rule. But when I plug in 0, I get 1 to the negative 1, and 1 to any power is 1, so I get 1. So my C naught is 1. When I take the first derivative, I'll bring down the exponent, take 1 away from the exponent, same inside, and then times the derivative of the inside. But the derivative of the inside is negative 1, so that makes this a plus 1. And so then when I plug in 0, this becomes 1 to the negative 2, and I just get 1. So C 1 is also 1. When I plug in 2 for 2, take the second derivative, bring down the exponent, negative 2, take 1 away from the exponent, times the derivative of the inside. But the derivative of the inside is negative 1, so that will make this minus 2 a plus 2. And so then when I plug in 0, I just get 2. And then 2 divided by 2 is 1. And when I plug in 3, then take the third derivative, bring down the exponent, negative 6, take 1 away from the exponent, negative 3 times the derivative of the inside, 6. Plug in 0, and all of this becomes 1 times 6, 6. And then 6 divided by 3 factorial, 3 factorial is 6, and you're just going to get 1. when you do 4, you're going to bring down the, ooh, didn't do that right. So that should be it, took one away from exponent negative 4. You're going to bring down the negative 4, and you're going to get negative 24 times 1 minus x times the derivative of the inside, which is negative 5, and this is going to be a plus. And so you're going to get 24. And then you're going to get 24 divided by 4 factorial. But 24 is 4 factorial, and so your answer is 1 again. It seems like all of your coefficients are always 1. So that means then that Pn of x will just be 1 plus x squared plus x cubed plus x to the 4th plus dot dot dot. All your coefficients are 1, so you're just going to get x to the nth. And so then this is a pretty simple to write in summation notation, right? We start with 0 from k equals 0 to n, and then we have x to the k. Right, there we go. Find the nth Taylor polynomial about x equals 1 and express it in summation notation for the function f of x equals 1 over x. So here we have n. Fn of x, Fn of 1. This is a Taylor polynomial, so it's not a Maclaurin polynomial. We're not plugging in 0, we're plugging in 1. And then Cn. So when n is 0, we're dealing with x to the negative 1. And then we get plug in 1, 1 to any power is 1. And so then C1 is 1. When n is 1, take your first derivative, bring down the exponent, take 1 away from the exponent, and then when you plug in 1, 1 to any power is 1. And so your C1 is minus 1. Remember the formula for this is Fn of 1 divided by n factorial. So when n is 2, you're going to have 2 x to the negative 3. 1 to any power is 1. You'll get 2. And then here you will get 2 over 2 factorial, which is 1. When n is 3, you will get 6, negative 6, x to the negative 4. And then when you plug in 1, you will get negative 6, because 1 to any power is 1. And then over here, negative 6 over 3 factorial is negative 1. When n is 4, you will get 24, x to the negative 5. And then over here, you'll plug in 1 and you'll get 24. But 24 divided by 4 factorial is positive 1. So again, pretty easy pattern to see, and you can see why this is going on. You keep bringing these down and you keep getting the factorials here. This is 0 factorial, 1 factorial, 2 factorial, 3 factorial, and 4 factorial. And so then since you're dividing by the factorials, you're just going to constantly keep getting a 1. So then P sub n will just be, but it's not a polynomial in x, it's a polynomial in x minus 1. So then P sub n will be 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed, and so on. And then in summation notation, we'll start with 0, k equals 0 to n, and then we have this alternating factor, so we'll have the negative 1, and it starts positive, but we're starting at 0, so it's just k, and then x minus 1 to the k. And there you go. So your homework for this section is right here, 17 through 31 odd and 39 through 43 odd. Okay, that is it for this section. We move on to the next section.